So, chapter 1 of the fluid mechanics. So, first of all, in this class, you know that this is fluid mechanics, so we need to know the definition of the fluid. So, but let me first, before getting to that, I just wanted to make sure that you know that this pre-written lecture notes gonna be in the UWeLearn, so you can download it and fill it with me once I'm teaching, or you can just have it, I don't know, in your iPad, on your tablet, and writing on it. So make sure that you have this in front of you. So, what is a fluid? A fluid is defined as a substance that deforms consequently when acted on by a shearing stress of any magnitude. So let me just write it down. So a fluid is defined as a substance that deforms due to a shearing stress continuously when acted on by a shearing stress of any magnitude, right? So this is the definition, and when studying the behavior of a fluid, typically consider average characteristic, I mean macroscopic, macroscopic. We need to consider the average characteristics over a small volume of many modules rather than individual molecular action, which this is called continuum approach. So this continuum approach, also there is a course on it in the graduate level, and it's actually a hard course. It's not that much easy, but it's okay. So when I'm talking about the shearing stress here, so the shearing stress is, first of all, is a force per unit area. So it's created, shearing stress is created whenever a tangential force acts. So shearing stress is created whenever a tangential force acts on a surface, which you can see on this picture. So now maybe you question, what is the difference between a solid and a fluid? So the solids like steel or I don't know, any metals are acted on when are acted on by a shearing stress they will initially deforms like just a very small deformation at the beginning, right? But then they will not consequently deform like a flow. So this is the difference between them. And but also remember that the both liquids and gases are fluids. So air is a fluid, water is a fluid, uh, oil is a fluid. So just remember that. Um, so dimensions when you are talking about um, mm, to describe something, some characteristic, you need to know the dimension. So because fluid can describe qualitatively, as we need some measurements or a certain basic to describe that qualitative by a quantity. So this is why we need dimensions. So it means that the qualitative aspect serves to identify the nature or the characteristic or the type like of the fluid. For example, if we want to know what is the velocity of the fluid, what is the length of it. So these are all qualitative aspect. So then it means that the qualitative aspect serves to identify the nature or type of a characteristic so like as I said, length, like time, like the stress that we just talked about it, and like velocity. So and the quantitative aspect, I don't know why I keep saying aspect, provides a numerical measure of the characteristic. So the quantitative provides a numerical measure of the characteristic. So we have some, we call it primary quantities because the other secondary quantities are based and created um, by using these primary quantities. So these quantities like length, which the symbol is L, time, the symbol is T, and then mass, which the symbol is M, and then temperature, oh I forgot to write it down, the symbol is theta. So these are we can use these quantity to provide the quality description of the fluid. So for example, if I want to just also uh, take some example for the secondary quantity, which is made from the basic dimensions. This is how it's gonna happen. So we know that area, right? We know that the area units is L2, right? Which is L squared, which has two basic dimensions. And then we have velocity, which the units are LT2 minus 1, which we know that velocity is x over t, which x is kind of a distance, so the unit gonna be meter, and then the time, which is t, we know that the unit is gonna be second. So these are the units, and if we want to just write down like a system, we have two systems actually. We have MLT system and FLT system. We're not talking about it in this chapter. It's gonna be in chapter 5. But what happened is that we know that this is mass, this is length, and this is time. And here, this is force, this is length, and this is time. So we can write down velocity as length per time, right? So this is how we just describe this secondary quantity. So for example, density, right? We know that density is mass per volume, right? Mass per volume. And then if we want to write it down in MLT system, it's gonna be mass, which is m, and L to the minus 3, right? So just be careful about this. I mean, just try to learn it, because we're going to use it in chapter 5. So I'm going to go in chapter 5, so I'm going to, teach it from scratch, so it's okay. So then we have another thing in the units that we call it dimensionally homogeneous. What it means is that, for example, if we have an equation like v equal to v0 plus at, which is the equation of velocity when it's a uniformly accelerated body. So then v0 is the initial velocity, and a is the acceleration, and t is a time. So in terms of dimensions, the equation gonna be, so velocity, we know that velocity is L t minus 1, right? The v0, which is the initial velocity, also is L t minus 1, right? And the acceleration, we know that acceleration is dv over dt, right? So it means that we know that v, so by the way, the operation, the mathematic operation is not, do not have dimensions. So this derivative doesn't have dimension. So we are just talking about v. It is L over t minus L over t, and then time, which is t, and then if we simplify that, it's gonna be Lt minus 2, right? So here we have LT minus 2, right? But just be careful. For example, this one and this one and this one should be exactly the same. Otherwise, we didn't kind of follow this rule, right? It's homogeneous. So we have another T here, and the time the symbol is T, right? If we simplify that, it's gonna be LT minus 1, which is exactly as it is. So remember that all of the dimension for these three should be the same. Okay. Then the system of units. So we have different system of units in I mean the in the world. So we have international system, we have British system, and we have English system. So in this book, we mostly using the international system SI. So if we compare the international system, British and the English system, so the length in SII system is meter. In the other two systems are food, food. So the time is second in three of them. The mass is a kilogram and it's a pound in the other system. The temperature we are using is Kelvin in the SI, and also we have force, energy, and power. So remember that when we have Newton, which is N, the 1 Newton is basically 1 kilogram multiplied by m, and I think I missed something here, which is s squared, and then joule is Newton meter, and watt is Newton meter per second. Just try to understand how we get these things. If you write down the formula for each of those, so you can see that how we get these units. And it's important you kind of understand and stick these units in your mind and memorize it. But first, before memorizing, just understand it. So then the other important thing in system of unit is that you cannot use one system and mix it to the other system at the same time. For example, if I want to just I don't know, I have a velocity of 5 meter per second. Let's talk about length. I have the length of, I don't know, let's say 2 meter, and then I have length for 3 foot. But when I want to, this is L1 and this is L2, and if I want to get L1 plus L2, I need to convert one of them to the other. For example, I can't convert this 3 foot to the meter and then add them together, or I can convert 2 meter to the foot and then add them together. So it should be just, remember, they need to both have the same unit. So this is about the system of the unit. So then after that, we are going to talk about the analysis of fluid behavior. So these are all going to be in the other chapter of the book. So these three gonna be in chapter 5, and then we're going to talk about it. Oh, this one is chapter, by the way. This is going to be in chapter 7. I don't know why I said 5. So this is chapter 7, and this is sorry, this is chapter 5. And also there is something else that we need to know about the fluid mechanic. So when we talk about fluids, there are two aspects of fluid. We can divide the problems to it. For example, if the fluid is at rest, or if the fluid is moving. So they are different in solving the problem on each of them. So we're gonna talk about it in the future chapters. So don't worry about it. We're gonna talk about it, and then I just wanted to tell you that because we need, when we want to solve a question, we need to know what approach we need to take. So we need to make sure, we always just do the subdivided to make it easier for understanding the question and solving it. So these are just the two main subdivision for the fluid mechanics. So let's talk about some of the variables for the fluid mechanics. So we have density, and density is just called, so these are actually the kind of common properties that it's in the fluid mechanics. So the density is mass per unit, which the formula is rho m over v. This is volume. So in this book, when we want to write volume, we're gonna writing it like that, and if we write it this way, it's gonna be velocity. So and if I want to write down the unit is kilogram over meter cubic, and a specific volume is volume per unit. So then it means that nu is, this is a specific volume, is volume per mass, and then it means that it's 1 over rho, right? Because density is mass per volume, and then so the unit gonna be the unit gonna be meter cubic per kilogram. So the specific weight, the weight is the specific weight is weight per unit volume, and this is the Greek symbol we are using for the specific weight, and then gamma is equal to rho g, and the units is Newton per meter cubic, right? So another characteristic of the fluid that I'm going to talk about it is specific gravity. So specific gravity is the ratio of a fluid density to that of water. So it means that, for example, if we have a G, which is a symbol of specific gravity, we have the density, right, of that fluid over the density over the density of the water at a temperature. So this temperature, which is a specific temperature, should be 4 degrees centigrade, and the density of the water at 4 degrees centigrade H2O is approximately 1000 kilogram meter cubic. So if we want to know the specific gravity of a special fluid, we just need to know that the density of that fluid, because this one is always the same thing, right? So, so we talk about the fluid mass and weight. And now we're going to talk about the ideal gas law. So the ideal gas law, I'm not sure if you guys pass and take the thermodynamic or not, but it's basically more talking, we more talking about the ideal gas law in the thermodynamic. But just to get to it and just mention it, when the ideal gas law relates the change in density to changes in pressure and temperature. So if we look at the formula, which is P equal to rho RT, so first P is absolute pressure, is the absolute pressure, rho is density, R is gas constant, and T is the absolute temperature, right? So when we say that ideal gas, it means that this formula, that when we are using this formula, it just approximates the behavior of real gases under the normal conditions. So that's it for the ideal gas. I'm not going to just talk about it too much. Let's go to the viscosity, which is one of the most important things in this chapter. And remember that when we are talking about ideal gas, we need to use the absolute pressure and temperature. So, viscosity. So, what is a viscosity? If we when we are talking about the fluid, if we say the density of the fluid is that, the specific volume is that, or the other thing that we just talk about it, right? That it just shows the heaviness of the fluid. But we always need to know the fluidity of a fluid. So viscosity can describe it. This is why we need viscosity. So consider this figure. So if a fluid between these two plates, if we move, if this plate, this is a plate, right? And this is a plate. Where the lower plate is fixed, and the upper plate, uh, a force or a pressure is applied to the upper plate, it's gonna cause fluid to move continuously with the velocity of the plate. So it means that because if I just draw it here, we have two plates here. This is fixed, right? And this is moving by the velocity of u. We actually apply a force to move this plate. So there is liquid here, right? Which let's say this is there is water here. So if we if this plate is moving with velocity of u, then this fluid is moving with velocity of u. And this fluid right here, which is attached to the fixed plate, the velocity of the fluid attached to the plate is 0, right? So this is one condition, one important condition in the fluid mechanics. It means that the real fluids, even though they may be moving, always stick to the solid boundaries that contain them. It means that they have the velocity of the solid boundaries at the boundaries. So, and then this is how I mean, the other velocity of the fluid at the other location is half. So it just starts from 0, which is the fixed plate, and go top to get the maximum velocity of u. So this is a viscosity. Think about it more, just if you want to look at some videos on viscosity, it's okay, just take some time, because I think it's new definition for you guys. Just take your time to just understand what's going on between the thing. But the important thing is this it's this phrase. So it's in, oh man, the important thing is this sentence. So just remember that it's always have the solid boundaries. Let's see what is the, so we have two definition also. We say that a rate of shearing stress, this is the definition of the shearing rate of the shearing stress, and the shear stress. So mu du dy, right? And so let me say this need to find. So, and mu, I forgot to tell you what is mu. Mu is a property of the fluid, and we call it absolute viscosity, or also we call it dynamic viscosity, or they are just call it viscosity. We have also another viscosity, which is called dynamic viscosity, which is mu over rho. So just remember that this is always, we call it dynamic viscosity, but mu we can call it viscosity as well, and the unit is gonna be different. So this is gonna be N2 over S, you can just write down the unit of density and mu to get the unit of the dynamic viscosity. And let's see what else we have here. Um, I think that's it for here. I'll talk about this. Okay, so let me just talk about it a little bit more. Just I wanted to make sure that you understand that this velocity gradient, which is du over dy, develops in the fluid due to a viscous effect. So this is what I wanted to say about that as well. Yeah, that's it. And then you can also derive that units. So maybe you just pause the video, derive it, and then compare it to mine. So we know that this is u, this is velocity. So it's gonna be meter per second, right? And this is why we should be meter. So this gonna cross out. So it's gonna be 1 over s. So this is the unit for s2 minus 1. So I think we talk about, yeah, we talk about these properties. So let's talk about the fluids. So we have another subdivision for fluid. We have two kind of fluid. We call it Newtonian fluids or non-Newtonian fluids. So when we say that a fluid is a Newtonian fluid, it means that the shear stress is linearly related to the shear rate, I mean the rate of change of velocity, which is du over dy, right? So if I just draw it and wanted to show you here, if this is tau, which is shearing stress, and this is du by dy, when it's Newtonian, it's gonna be linearly, right? And then it's not, I don't know how. I'm so bad at drawing, sorry. Let me just try it one more time. Okay, now it's good. So this is, it just, now it's these two properties is linearly related to each other. So this is a Newtonian fluid. The example gonna be, let's say, for example, water, some of the oil, and air also. These are Newtonian fluids. So when we want to talk about the non-Newtonian fluids, and these are actually three types of non-Newtonian fluid, but the main difference between the Newtonian and non-Newtonian fluids is that the shearing stress is not linearly related to the rate of shearing stress. So this is how we describe the non-Newtonian fluids. So if we want to talk about the shearing thinning fluid, which is um, one of the non-Newtonian fluids. Uh, it's it happened the way that the viscosity appears to increase as the shear rate increases. So it starts off thin, right? And then um, as you just increase the the shearing stress, it's gonna be thicker and thicker. So this is how we just define it. And then it means that the harder fluid is sheared, the less viscous it becomes. So like for example, if we think about it, like ketchup, right, or blood, or paint, and the other one is shear thickening fluid. And in this is, if we want to look at the chart, this is the shearing and thickening. It means that the harder the fluid is sheared, the more viscous it becomes. And if I and the example gonna be um, the quicksand or silly putty. So these are the example for this one. And then when we want the other one of the another kind of the non-Newtonian fluid is Bingham plastic. The Bingham plastic is in a way that when, for example, um, we need it requires a certain minimal stress on it before it will start to flow. So instead of flowing immediately, you have to push on it by some amount, and then it will start flowing like a fluid. Um, this is how, for example, we think as Bingham fluid. If you think, for example, we have a bottle of, let's say, mayonnaise. So you need to first um, create an initial and a sufficient shearing stress in order to allow the mayonnaises to start flowing. Another good example of it is toothpaste. So, and mayonnaises. So these are the example for the different type kind of non Newtonian fluid. In this book, we mostly, yeah, I mean, it mostly the Newtonian fluids we applied them more. And let me see. I talked about everything that I wanted. So I'm going to solve some question for this chapter. I'm going to solve it in the class. Then I'm gonna record the video of it. So see you.